In this video we're going to be having a look at the timing diagrams of flip-flops or sequential logic circuits. And the flip-flop that we're going to be looking at specifically is the JK flip-flop, named after its inventor, Jack Kilby. And it looks just like this. We've got J and K inputs, we've got a clock input, and then we have our Q and Q bar coming out. Okay, our J is sort of like our set, and our K is sort of like our reset. And basically it's just the combination of a SR latch and a little clever clocking circuit. Well, let's have a look at the way it operates. We have our clock, J, K, Q of T plus 1, and I'm going to skip the not Q just to keep it simple in this example. Alright, now when I use the term Q of T plus 1, what I'm actually saying is Q at the next clock edge, whether that may be rising or falling edge. Right? So Q of T is now the current output, Q of T plus 1 is Q of T at the next clock edge. So if I enter my clock edges like this, up arrow, all meaning rising edge, 0, 1, and down arrow meaning falling edge. I'm going to enter my possible combinations for J and K, as well as our don't care states. And I'm going to enter in what happens. So, rising edge on the clock, this is rising edge triggered, no bubble there. Okay, no J, no K, both of them are active high. Okay, both inputs are 0. We have no change. So the next output is the same as the current output, Q of T. Function is no change. For a rising edge of the clock, when set, or J is low and K is high or active, we get the output going to 0, effectively a reset. When we get J is high and K is low with a rising edge of the clock, then the output goes high. So you see in both of these ones, it's irrespective of what the previous input is, okay, or sorry, the previous output, it's a forced change. Okay, so that would be our set. Now this one, we're 1 and 1. If we remember in the SR latch, a 1 and a 1 gave us this forbidden state, okay, for an SR latch. Now the JK flip-flop gets around this, and due to its clever circuitry, actually has this effect, not QT, or toggle. So both 0, 0 and 1, 1 on our J and K inputs both have memory of the previous output, except when they're both high, you get a toggling action. When the clock is 0, nothing happens. When the clock is 1, nothing happens. It's rising, falling edge, nothing happens. Okay, so no change. It's just going to remember its previous state. Right, so this is the JK flip-flop, and it's one of the more common ones. This one's known as the synchronous JK flip-flop, as it has no asynchronous inputs, which we're going to see very shortly. So let's have a look at the example of filling in a timing diagram with the JK flip-flop. Now I'm just going to scrub out, we don't want that falling edge. Okay, that's wrong, sorry, in this example. This one is rising edge, okay, because it has no bubble on that input. Alright, so we're interested in all of these rising edges as we have here. So drawing Q, starting from the bottom, rising clock edge, J is 1, K is 0, is a set, and following through to the next rising clock edge, J is 0, K is 0, J is 0, K is 0, it's a no change. Next clock edge, both 0, still no change, carry on through. K is now active and J is not active, so that's the reset condition. Next clock edge, no change, no change. Okay, this is set. Set again. Now we have both active, so it's a toggle. Coming through, toggle again, toggle again, toggle again, and so forth. Now one of the things that may be quite nice to do as you're going through this is above each clock edge to write what operation that you performed. J is 1, K is 0, so we did a set. I'll just do this a little bit higher. Set, no change, no change, reset, and this one was no change, no change, set, set again, and sorry, that was not no change, that one was a toggle, 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 toggle. Right, so perhaps you might want to do that part first, or perhaps you draw the diagram, but it's a good way of checking that everything you've done is correct. Alright, moving forward, let's have a look at the application of 3 cascaded JK flip-flops. J0, K0, J1, K1, J2, K2. Clock, clock, clock inputs. Q0, Q1, Q2. And we're going to cascade these. And for all of our J and K inputs, they're going to be set up as 1s. So all of these JK flip-flops, and we know they're JK because the J and K names on the inputs, are set up as in toggle mode permanently, and we're just cascading the outputs through these flip-flops. So let's have a look at how that would work in a timing diagram. Remembering that all of these are going to toggle. So let's start with Q0. We're going to start at the bottom. Alright, what we're going to do actually is use falling edge triggered flip-flops here, only because it makes it a little easier to understand. And what I'm also going to do is draw little arrows on each of our falling edges. That will help us when we come through to actually drawing this. Last step is also a couple of construction lines, once again to help keep everything in sync together. So starting, from Q0 this time, we come over to first edge, we're going to toggle, next edge, toggle, toggle, and so forth coming through. Right, noting that this is half the frequency of the original clock frequency. Now we're looking at the falling edges of our Q0 output, because that comes into our clock line of our Q1. So now we toggle, 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 seeing how our construction lines help out as well. Now we've only got 2 edges to toggle on for our final one. So if we have a look now, what we can see, if we actually write down the states of each of these lines, is you'll start to build up a picture of a counter. And if you take alpha, Q0, Q1 and Q2, noting that Q2 is our most significant bit versus Q0, which is our least significant bit. And if I write down the numbers underneath this, reading this in binary, we'd get 0, 1, 2, 3, 4, 5, 6, 7, and then back to 0. So what you see is that this particular circuit, which is simply 3 JK flip-flops set up to continuously toggle, has become a 3-bit up counter, which is quite a nice exercise that we go through in the next video of how you would actually put these together. Alright, so 3-bit up counter using only JK flip-flops. Let's then have a look at the asynchronous JK flip-flop. Alright, so the symbol for an asynchronous JK flip-flop looks very similar, except we have a couple of extra inputs. We have a reset, or I should call it clear, a preset, as well as our normal, just make that a little bit bigger, Q and Q bar outputs. Alright, so very similar to what we've seen before, except we have these 2 asynchronous inputs, and we're going to see why they're asynchronous when we have a look at the truth table. So we've got preset and clear, both active low because they've got those bars above them. Oh, can't forget my clock. Clock, J, K, Q of t plus 1, and function. So let's fill in the operation of our JK flip-flop with asynchronous inputs. Now you'll note that the asynchronous input configuration, provided that we're not in the both inactive, remembering that they're both active low, down here it operates just as we've seen before. Okay, it operates as a synchronous JK flip-flop. But if any of the asynchronous inputs are active, so anywhere we see zeros at the moment, then regardless of what the synchronous inputs are doing, JK or the clock, the operation is going to change. Alright, so these ones actually have priority. Priority over the synchronous inputs. So our preset when active, our clear when active, and we also have back to a forbidden state. We can't preset and clear at the same time. Preset, set, or following the name, preset. So we have ways that we can preload our JK flip-flop with a value, for example output of 1 using the preset input. We can clear it at any time if we want to. We avoid that forbidden state. Otherwise, if they're both not active, Alright, in this case both 1s because they're both active low. Then it functions exactly as we saw previously up here. Alright, so it follows that same pattern as before. So let's do an example to see what that would look like. In this case, I'm going to add a circle there to our clock input. So I'm going to change this into a falling edge sensitive JK flip-flop. Alright, and that will match our diagram a little better here. So in all of these cases, we're looking at the falling edges. Now, you'll note that Q has started high. Excuse me. So let's have a look what happens. Both preset and clear are 1 and 1 at this point, so neither of them are active. J and K are both low, so we get a no change in the synchronous row. And so what I'm going to do this time is I'm going to go through first of all and write in all of the changes. Alright, the next one we've got a reset. Then we've got at this point here, so the next one we have is our preset going active. So I'm just going to put a P for preset here. Then we would have normally a reset with our clock, but because the preset active, that's not going to do anything in this case, but I'll still put it there anyway. Following along again, we've got another reset. Our preset is no longer active. Then we have another preset, then a no change, then another no change, then we get a clear, then we get another no change, then we get J going high, so we have set, set again, and we get our clear. We would have another set, but clear is still active, and we've got a no change, and then we have toggle, toggle, toggle. Right, so reasonably complicated example, but let's have a look at what it looks like then when we draw it. So for the first edge we have a no change, through to then we have our reset, 0 and a 1 on the reset. Then remember, our asynchronous inputs don't have to be synchronous to the clock, they can happen at any time. We have a preset going active, remembering they're active low. Carry on forward. Normally we'd have a reset on the next clock edge, but the asynchronous inputs take priority, so we continue on to the next edge or the next change of the preset. Okay, we don't suddenly go back to 0 if the preset's no longer active. It's a sequential device that has memory, so it holds its state. Okay, now we have K high, so we have a reset. Then we've got another preset active. Then we have a no change through to a clear. And another no change. Oh. Through to now a set, synchronous set this time, synchronous set again, clear goes active, we have a synchronous set but we also have a clear, asynchronous clear, so we remain down, then we have a no change, 0, 0, 1, 1, and then toggle, toggle, toggle. Alright, so brief summary again, looking at timing diagrams with respect to our JK flip-flop. Okay, JK flip-flop, just remember the J is the set, and the K is the reset terminal. By default it's synchronous if we don't see any other inputs in it, and we get this operation here. Okay, in this case this one, because there's no bubble here, is rising edge triggered. J function is the set, K is the reset. If they're both high, and remember this, we get this toggling operation, and if they're both low, no change, it remembers it, being a sequential device, and we did work through that example here. Obviously the not Q output is easy to draw because you can just do the inverse of what you did for the Q. We also looked at the placing JK flip-flops in series so that we could, when configured in a toggle mode, actually create a 3-bit counter, as we saw when we completed the timing diagram. And then finally we had a look at the JK flip-flop with asynchronous inputs, the preset and clear, noting that those had priority over the synchronous inputs. So regardless of what the clock or JK were doing, the outputs would change based on those. And remembering that we have that forbidden state. And then going through the example, we saw how things are a little bit more complicated and just having to watch out for when the preset and clear occur to be able to work out what our output was doing.